Hey dear, welcome to one another video on our community for developers. Today we will deep dive into high-level and low-level system design and software architect of Netflix. So what is Netflix? Netflix is a subscription-based streaming service that allows its members to watch TV shows and movies on an internet-connected device. It is available on platforms such as the web, iOS, Android, TV, etc. Requirements. Our system should meet the following requirements. Functional requirements. Users should be able to stream and share videos. The content team, or users in YouTube's case, should be able to upload new videos, movies, TV shows episodes, and other content. Users should be able to search for videos using titles or tags. Users should be able to comment on a video similar to YouTube. Non-functional requirements. High availability with minimal latency. High reliability. No uploads should be lost. The system should be scalable and efficient. Extended requirements. Certain content should be geo-blocked. Resume video playback from the point user left off. Record metrics and analytics of videos. Estimation and constraints. Let's start with the estimation and constraints. Traffic. This will be a read-heavy system. Let us assume we have 1 billion total users with 200 million daily active users, DAU, and on average, each user watches 5 videos a day. This gives us 1 billion videos watched per day. 200 million 5 videos equals 1 billion per day. 200 million 5 videos equal 1 billion per day. Assuming a 200:1 read-write ratio, about 50 million videos will be uploaded every day. 1200 I 1 billion equal 50 million day. 2001 pi 1 billion 50 million day. What would be requests per second, RPS, for our system? 1 billion requests per day, translate into 12K requests per second. 1 billion 24 hours times 3,600 seconds equals 212K requests per second. 24 hours, 3,600 seconds. 1 billion 12K requests second. Storage. If we assume each video is 1 hugs on average, we will require about 5 PB of storage every day. 50 million 100 MB equal 5 PB per day. 50 million 100 MB equal 5 PB day. And for 10 years, we will require an astounding 18,250 PB of storage. 5 PB 965 days, 10 years, 18,250 PB. 5 PB 65 days, 10 years, and 18,250 PB. Bandwidth. As our system is handling 5 PB ingress every day, we will require minimum bandwidth of around 58 gigabits per second. 5 PB, 24 hours, 600 seconds equals 258 gigabytes second. 24 hours, 3,600 seconds. 5 PB equal 58 gigabytes per second. High-level estimate. Here is our high-level estimate. If you have seen our high-level estimate, we will cover the next topic. We will cover the entire topic into following parts. Part 1, Data Model Design. Part 2, API Design. Part 3, Netflix Main Components. Part 4, How Netflix Onboard a Movie. Part 5, Front-End and Back-End Development. Part 6, Microservices. How API Gets the Response. Part 7, How Netflix Recommendations System Works. Part 8, High-Level Design. Part 9, last but not the least, Resolving Bottlenecks. So let's not waste our time and get into Netflix system design. So let's first deep dive into data models design. Make sure you need the requirements. We have the following tables. Users. The table will contain a user's information such as name, email, date of birth, and other details. Videos. As the name suggests, this table will store videos and their properties such as title, stream URL, tags, etc. We will also store the corresponding user ID tags. The table will simply store tags associated with a video. Views. The table helps us to store all the views received on a video. Comments. The table stores all the comments received on a video, like YouTube. What kind of database should we use? While our data model seems quite relational, we don't necessarily need to store everything in a single database, as this can limit our scalability and quickly become a bottleneck. We will split the data between different services, each having ownership over a particular table. Then we can use a relational database such as PostgreSQL or a distributed NoSQL database such as Apache Cassandra for our use case. Before designing our API, we must first deal with design. As in API designing, we will dive into parameters for streaming video. Video ID, UUID, ID of the video that needs to be streamed. Parameters query string, search query from the user. Now that you are okay with the data model design, you must remember the table we have taken, as we are going to revolve around it. Let's now jump into API design. Next, we are diving deep into designing the API. We will mostly deal with 4 API. One for uploading video, which act as a byte stream that enables this API to upload video to our services. It's read as upload video, title string to string, data, stream byte, tags, string boolean. It's include parameters that contains title, string, title of the new video. Description, description of the new video. Data, byte, byte stream of the video data. Tag, string, tags for the video, optional. Returns result boolean, represents whether the operation was successful or not. Next, we are streaming a video. For that, we are going to need a different API that allow users to stream a video with the preferred codec and resolution. Stream video, video ID, code enum string resolution, tuple int, off video stream. This include parameters like video ID, ID of the video that needs to be streamed. Codec, enum string, required codec of the requested video, such as H.265, H.264, VP9, etc. Resolution, tuple int, resolution of the requested video. Offset, int, offset of the video stream in seconds to stream data from any point in the video, optional. Return stream, video stream, data stream of the requested video. The next API will enable our users to search for a video based on its title or tags. Search video, query string, next page string. It include the parameter as query string, search query from the user. Next page string, token for the next page. This can be used for pagination, optional. Returns videos, video, all the videos available for a particular search query. The last API that we are going to design is nothing but our comment API. This API will allow our users to post a comment on a video like YouTube. Comment, video ID, comment string, boolean. The parameters include the video ID, ID of the video user wants to comment on, comment, string, the text context of the command, which returns the result, boolean. Represents whether the operation was successful or not. With this, we will wrap our API designing part. We will cover in much details once we get into high-level design architecture. We will cover some advanced topic like chunking a file, video processing, content filter, transcoder, video streaming, etc. But before that, you must know about the components of Netflix architecture. Next topic, that is the part 4 of our video, will be how Netflix onboard a movie. Before any movie is made available to users, Netflix must convert the video into a format that works best for your device. This process is called transcoding or encoding. Transcoding is the process that converts a video file from one format to another to make videos viewable across different platforms and devices. Why do we need to do it? Why can't we just play the source video? The original movie video comes in a high-definition format that's many terabytes in size. Also, Netflix supports 2,200 different devices. Each device has a video format that looks best on that particular device. If you're watching Netflix on an iPhone, you'll see a video that gives you the best viewing experience on the iPhone. Netflix also creates files optimized for different network speeds. If you're watching on a fast network, you'll see the higher quality video than you would if you're watching over a slow network. And also depends on your Netflix plan. That said, Netflix does create approximately 200 files for every movie. That's a lot of files and processing to do transcoding. Now we have all the files we need to stream it. OC Open Connect comes into picture. OC is Netflix-owned, no third-party CDN. What are the advantages of Open Connect? Advantages of Open Connect: less expensive, better quality, more scalable. So once the videos are transcoded, these files are pushed to all of the OC servers. Now the second scenario, when the user loads Netflix app, all requests are handled by the server in AWS. Login, recommendations, homepage, user's history, billing, customer support, etc. Now you want to watch a video when you click the play button of the video. Your app automatically figures out the best OC server, best format, and best bitrate for you. And then the video is streamed from a nearby Open Connect appliance, OCA, in the Open Connect CDN. The Netflix apps are so intelligent that they constantly check for best streaming server and bitrate for you, and switches between formats and servers to give the best viewing experience for you. Now, what Netflix does is with all of your searches, viewing, location, device, reviews, and likes data on AWS, it uses Hadoop, machine learning models to recommend new movies which you might like. And this cycle goes on and on. Netflix supports 2,200 different devices, including smart TV, Android, iOS, gaming consoles, web apps, etc. All this make the Netflix streaming smooth and efficient. We will get to the tech stack on our next part, that is the part 5. Before we deep dive into tech stack of Netflix, you must consider Netflix have a quite busy design. We will break it into following: front-end, languages, framework; back-end, languages, which cloud service, why microservices, other components like Zool, Hystrix, stateless service, databases, why NoSchool, Cassandra. So in case you are hearing the tech stack for the first time, that's not a big deal as you are talking about a billion-dollar system design. Netflix React.js. React was influenced by a number of factors, most notably 1. Startup speed, 2. Runtime performance, and 3. Modularity. For the cloud service, Netflix uses Amazon's Elastic Load Balancer (ELB) service to route traffic to our front-end services. ELBs are set up such that load is balanced across zones first, then instances. This is because the ELB is a 2-tier load balancing scheme. The first tier consists of basic DNS-based round-robin load balancing. This gets a client to an ELB endpoint in the cloud that is in one of the zones that your ELB is configured to use. The second tier of the ELB service is an array of load balancer instances, provisioned directly by AWS, which does round-robin load balancing over our own instances that are behind it in the same zone. Zool. The netty handlers on the front and back of the filters are mainly responsible for handling the network protocol, web server, connection management, and proxying work. With those inner workings abstracted away, the filters do all of the heavy lifting. The inbound filters run before proxying the request and can be used for authentication, routing, or decorating the request. The endpoint filters can either be used to return a static response or proxy the request to the backend service, or origin, as we call it. The outbound filters run after a response has been returned and can be used for things like gzipping, metrics, or removing custom headers. Features: supports HTTP2 mutual TLS, adaptive retries, concurrency protection for the origin. It helps in easy routing based on query params, URL, path. The main use case is for routing traffic to a specific test or staging cluster. So Netflix redesigned Data Storage Arch with 2 main goals in mind: smaller storage footprint, consistent read-write performance as viewing per member grows. So the solution: compress the old rows. Data was divided into 2 types: live viewing history, live VH, small number of recent viewing records with frequent updates. The data is stored in uncompressed form as in the simple design detailed above. Compressed viewing history, compressed VH, large number of older viewing records with rare updates. The data is compressed to reduce storage footprint. Compressed viewing history is stored in a single column per row key. Kafka to Chukwa for distribute system monitoring. Push all the Netflix events to processing pipelines, 500 billion events and by 1.3 PB per day. 8 million events and 24 GB per second during peak hours. What kind of events? Video viewing activities, UI activities, error logs, performance events, troubleshooting and diagnostic events. Apache Chukwa plays an important role in his system. Design. It is an open-source data collection system for monitoring large distributed systems. Apache Chukwa is built on top of the Hadoop Distributed File System, HDFS, and MapReduce framework, and inherits Hadoop's scalability and robustness. Apache Chukwa also includes a flexible and powerful toolkit for displaying, monitoring, and analyzing results to make the best use of the collected data. The Kafka routing service is responsible for moving data from fronting Kafka to various sinks, S3, Elasticsearch, and secondary Kafka. Routing is done using Apache Samza. When Chukwa sends traffic to Kafka, it can deliver full or filtered streams. Sometimes we need to apply further filtering on the Kafka streams written from Chukwa. That is why we have the router to consume from one Kafka topic and produce to a different Kafka topic. Next is the Elasticsearch. We have seen explosive growth in Elasticsearch adoption within Netflix for the last 2 years. There are 150 clusters totaling 3,500 instances hosting quite 1.3 PB of data. The vast majority of the data is injected via our data pipeline. How it's used at Netflix. Say when a customer tried to play a video and he couldn't, he calls the customer care. Now how customer care guys can debug what's happening. So playback team uses Elasticsearch to drill down the problem and also to understand how widespread is the problem. To see sign-up or login problems. To keep track of resource usage. Other tech stack that must be taken care of are the media processing while onboarding and later validating the video. The first thing Netflix does is spend a lot of time validating the video. It looks for digital artifacts, color changes, or missing frames that may have been caused by previous transcoding attempts or data transmission problems. The video is rejected if any problems are found. After the video is validated, it's fed into what Netflix calls the media pipeline. A pipeline is simply a series of steps data is put through to make it ready for use, much like an assembly line in a factory. More than 70 different pieces of software have a hand in creating every video. Archer is an easy-to-use MapReduce style platform for media processing that uses containers so that users can bring their OS-level dependencies. Common media processing steps, such as mounting video frames, are handled by the platform. Developers write 3 functions: split, map, and collect, and they can use any programming language. Archer is explicitly built for simple media processing at scale, and this means the platform is aware of media formats and gives white-glove treatment for popular media formats. For example, a ProRes video frame is a first-class object in Archer, and splitting a video source into shot-based chunks, 1, is supported out of the box. A shot is a fragment of the video where the camera doesn't move. It's not practical to process a single multi-terabyte-sized file, so the first step of the pipeline is to break the video into lots of smaller chunks. The video chunks are then put through the pipeline so they can be encoded in parallel. In parallel simply means the chunks are processed at the same time. There is one more tech stack you need to emphasize on is the Archer. For example, a ProRes video frame is a first-class object in Archer, and splitting a video source into shot-based chunks is supported out of the box. A shot is a fragment of the video where the camera doesn't move. Detecting dead pixels caused by defective digital camera machine learning, ML, to tag audio QC for subtitles. If you want to get your hands on some fundamentals, feel free to check the description. We will provide some link to learn audio and media processing with machine learning framework like PyTorch. With these, we have almost covered the tech stack of Netflix architecture. We will cover how the system recommends movies with same genre. In the next part, detecting dead pixels caused by defective digital camera machine learning to tag audio QC for subtitles. If you want to get your hands on some fundamentals, feel free to check the description. We will provide some link to learn audio and media processing with machine learning framework, like PyTorch. With these, we have almost covered the tech stack of Netflix architecture. We will cover how the system recommends movies with same genre in the next part. Now we are moving into how Netflix keep engaging the audiences with their content. Whenever you access the Netflix service, the recommendation system strives to help you find a show or movie to enjoy with minimal effort. It's estimate the likelihood that you will watch a particular title in our catalog based on a number of factors including your interactions with our service, such as your viewing history and how you rated other titles. Other members with similar tastes and preferences on our service, more info here. And information about the titles, such as their genre, categories, actors, release year, etc. In addition to knowing what you have watched on Netflix, to best personalize the recommendations, it also look at things like the time of day you watch, the devices you are watching Netflix on, and how long you watch. If you want to learn about movie recommended system, do feel free to check out the description to see it practice. The next topic is going to be on collaborative filtering. The collaborative filtering, CF, algorithms are based on the idea that if 2 clients have similar rating history, then they will behave similarly in the future. If, for example, there are 2 very likely users and one of them watches a movie and rates it with a good score, then it is a good indication that the second user will have a similar pattern. Content-based filtering. The content-based filtering, CB, aims to recommend items or movies that are alike to movies the user has liked before. The main difference between this approach and the collaborative filtering is that content-based filtering offers the recommendation based not only in similarity by rating, but it is more about the information from the products. Agarwal, 2016, i.e., the movie title, the year, the actors, the genre. In order to implement this methodology, it is necessary to possess information describing each item, and some sort of user profile describing what the user likes is also desirable. The task is to learn the user preferences and then locate or recommend items that are similar to the user preferences. Hybrid filtering is one new method. The hybrid methods are characterized by combining CF and CB techniques. I will provide some resources if you want to learn more about the hybrid architecture. Spark usage for the movie recommendation is in pivotal role for recommendation. Spark is used for content recommendations and personalization. A majority of the machine learning pipelines for member personalization run atop large managed Spark clusters. These models form the basis of the recommender system that backs the various personalized canvases you see on the Netflix app, including title relevance ranking, row selection and sorting, and artwork personalization, among others. Now let's deep dive into high-level system design on how things work behind the scenes. Architecture. We will be using microservices architecture since it will make it easier to horizontally scale and decouple our services. Each service will have ownership of its own data model. Before getting in, let's try to divide our system into some core services. Stream service. The tweet service will handle video streaming-related functionality. Search service. The service is responsible for handling search-related functionality. It will be discussed in detail separately. Media service. This service will handle the video uploads and processing. It will be discussed in detail separately. Analytics service. This service will be used for metrics and analytics use cases. What about inter-service communication and service discovery? Since our architecture is microservices-based, services will be communicating with each other as well. Generally, REST or HTTP performs well, but we can further improve the performance using gRPC, which is more lightweight and efficient. Service discovery is another thing we will have to take into account. We can also use a service mesh that enables managed, observable, and secure communication between individual services. Now let's get into video processing. There are so many variables in play when it comes to processing a video. For example, an average data size of 2-hour raw 8K footage from a high-end camera can easily be up to 4 TB. Thus, we need to have some kind of processing to reduce both storage and delivery costs. Let's discuss how this works. File chunker. This is the first step of our processing pipeline. File chunking is the process of splitting a file into smaller pieces called chunks. It can help us eliminate duplicate copies of repeating data on storage and reduces the amount of data sent over the network by only selecting changed chunks. Usually, a video file can be split into equal-sized chunks based on timestamps, but Netflix instead splits chunks based on scenes. This slight variation becomes a huge factor for a better user experience, as whenever the client requests a chunk from the server, there is a lower chance of interruption, as a complete scene will be retrieved. Content filter. This step checks if the video adheres to the content policy of the platform. This can be pre-approved in the case of Netflix as per the content rating of the media, or can be strictly enforced like YouTube. This entire step is done by a machine learning model, which performs copyright, piracy, and NSFW checks. If issues are found, we can push the task to a dead letter queue, DLQ, and send someone from the moderation team can do further inspection. If you're not aware of what is a dead letter queue, a dead letter queue is a queue to which other queues can send messages that can't be processed successfully. This makes it easy to set them aside for further inspection without blocking the queue processing or spending CPU cycles on a message that might never be consumed successfully. The streaming itself is a process which includes content filter, transcoding, quality conversion, Let's break it into simple languages. Transcoding is a process in which the original data is decoded to an intermediate uncompressed format, which is then encoded into the target format. This process uses different codecs to perform bitrate adjustment, image downsampling, or re-encoding the media. Quality conversion. This is the last step of the processing pipeline, and as the name suggests, this step handles the conversion of the transcoded media from the previous step into different resolutions such as 4K, 1440p, 1080p, 720p, etc. This allows us to fetch the desired quality of the video as per the user's request, and once the media file finishes processing, it will be uploaded to a distributed file storage such as HDFS, GlusterFS, or an object storage such as Amazon S3 for later retrieval during streaming. The last topic is video streaming. It is a challenging task from both the client and server perspectives. Moreover, internet connection speeds vary quite a lot between different users. To make sure users don't refetch the same content, we can use a Content Delivery Network, CDN. Netflix takes this a step further with its Open Connect program. In this approach, they partner with thousands of internet service providers, ISPs, to localize their traffic and deliver their content more efficiently. Netflix Open Connect is the purpose-built content delivery network, CDN, responsible for serving Netflix's video traffic. Around 95% of the traffic globally is delivered via direct connections between Open Connect and the ISPs their customers use to access the internet. Currently, Netflix uses the Open Connect appliances, OCAs, in over 1,000 separate locations around the world. In case of issues, Open Connect appliances, OCAs, can fail over and the traffic can be rerouted to Netflix servers. Additionally, we can use adaptive bitrate streaming protocols such as HTTP live streaming, HLS, which is designed for reliability and it dynamically adapts to network conditions by optimizing playback for the available speed of the connections. Lastly, for playing the video from where the user left off, part of our extended requirements, we can simply use the offset property we stored in the views table to retrieve the scene chunk at a particular timestamp and resume the playback for the user. Searching GAR. Sometimes traditional DBMS are not performant enough. We need something which allows us to store, search, and analyze huge volumes of data quickly and in near real time and give results within milliseconds. Elasticsearch can help us with this use case. Elasticsearch is a distributed, free and open search and analytics engine for all types of data, including textual, numerical, geospatial, structured, and unstructured. It is built on top of Apache Lucene. Trending functionality is based on top of the search functionality. We can cache the most frequently searched queries in the last n seconds and update them every m seconds using some sort of batch job mechanism. It's time to discuss our design decisions in detail. To scale out our databases, we will need to partition our data, hash-based partitioning, list-based partitioning, range-based partitioning, composite partitioning. This approaches can still cause uneven data and load distribution. We can solve this using consistent hashing. Consistent hashing is a distributed hashing scheme that operates independently of the number of nodes in a distributed hash table by assigning them a position on an abstract circle or hash ring. This allows servers and objects to scale without affecting the overall system. So lastly, we are finishing off by discussing bottlenecks for the system design. If you have stuck so far with us, you had come along a long way. So let's end this with some questions. Feel free to give your opinion in the comment section. What if one of our services crashes? How will we distribute our traffic between our components? How can we reduce the load on our database? How to improve the availability of our cache? Here is my point of view towards the problems, running multiple instances of each of our services, introducing load balancers between clients, servers, databases, and cache servers, using multiple read replicas for our databases, multiple instances and replicas for our distributed cache. So if you have stuck with us, make sure to give a thumbs up and keep sailing through the tech world. We'll see you in the next video. Keep rolling.